This is the pre-calculus video for section 5.1 day 2 about fundamental identities. We're still working on that monster objective of identify and work with trigonometric identities for basic trigonometric identities, the Pythagorean identities, the cofunction identities, and the odd-even identities. And then we'll get to simplifying trigonometric expressions using the above identities and solve trigonometric equations using trigonometric identities and properties of algebra. So this is all about, at this point, not trying to draw triangles, but figure out with the identities what we can get this to simplify to. So example 5 says simplifying by combining fractions and using identities. And you can see that I rewrote those Pythagorean identities above this so that we're keeping those in mind as we're working through them. Simplify the following trig expressions to a power of a single trig function. And again, our thoughts as we work through this are, well, if we see powers, then that's a really good thing, because if we see squareds, then we can start doing some substituting. So when I look at D, I'm looking at the numerator, and I see 1 minus sine squared x. And at first you think, well, that's not anything from our identities, but then you realize, well, sure it is, because if we subtracted sine squared theta over on the other side, it would say 1 minus sine squared theta, and that is equal to cosine squared theta. So this is cosine squared x in this case. And then on the bottom we have cosecant squared x minus 1, and I go up there looking for my cosecant squared, and I see the same thing going on. And I realize that, well, to make this happen, what I'd have to do is subtract the 1 from cosecant squared theta, and that would leave me with cotangent over there. So that means the bottom, the denominator, is cotangent squared of x. So there's our first step. All right, so far we had cosine squared x over cotangent squared x. And now I have to decide, well, where do I go from here? And I see that I have the primary trig function of cosine, but I have a secondary trig function of cotangent. And I remember, you know what? It's always easier to see things in terms of just cosine and sine. So what I'm going to do is I'm going to rewrite cotangent squared x as cosine squared x over sine squared x. And hopefully when you see that, you think, oh, yep, look what's going to happen here if we multiply by the reciprocal. Cosine squared x will cancel out. We'll have 1's up there, and sine squared x over 1 is sine squared x. So there it is. So again, there are lots of different methods, and when we're done, we'll kind of run all together with them and say, you know, always try this, then try this. One of the definites with first-year trig students is going to be try to get everything in terms of cosine and sine and go from there, because usually you can see what's going on when you've done that. Now I better give myself a little space here for E. E is another one where after you've done several of these types of problems, you realize they're trying to hide something by separating those two fractions. So what I need to do is just take care of being able to do the subtraction, which would mean I need to come up with a common denominator. But first things first, we don't want to forget that this is subtraction. But we're going to need to change this to adding a negative sign of x so that we don't accidentally make a negative mistake when we're working on our least common denominator. And our least common denominator for this is going to be both the cosine of x and 1 minus the sine of x. So that means that the first fraction is going to be multiplied by cosine of x on the top and the bottom, which is good because that's going to create a cosine squared x in the numerator. So good news, let's keep going with it. And then we have to multiply the second one by 1 minus the sine of x on the top and the bottom. And just, you know, think about what those steps are going to create, and that you'll start to get some squareds. So my first little fraction is now cosine squared of x over cosine of x times the quantity 1 minus the sine of x. plus, and now if we distribute the negative sign of x, we'll have negative sign of x. I was going to write it backwards right now, but I shouldn't do that. I don't want to lose anybody. Negative sign of x plus sine squared x over cosine of x times 1 minus sine of x. So what we've done so far is just to figure out how do we get these two so that they have an LCD. And once they both have that same denominator, it's a common denominator, and we can go ahead and add. So up there in the numerator, I have cosine squared x minus sine of x plus sine squared x all over cosine of x times the quantity 1 minus the sine of x. And I notice, wait a second, squareds. Cosine squared and sine squared. Hey, when you add those two, that's a 1. So this is 1 minus the sine of x over cosine of x times 1 minus sine of x. Hey, that subtraction down there is broken into a piece that's made of multiplication with that 1 minus sine of x times cosine of x. That means I can think of these as factors in the numerator and the denominator, and these are going to cancel. And I'll have 1 over the cosine of x. Now, I don't want reciprocals. This was supposed to be simplified, so I think reciprocal for cosine, that's secant. And this big whopper simplified all the way down to the secant of x. So again, another strategy. If they give you two separate fractions, you probably need to see what they are as one big fraction in order to figure out which of those trig identities to use and how to go forward. And now I knew I was going to run out of space, so I went ahead and put f down here where it would be a little bit more accessible and give me a little bit more space. So for f, I take a look at it and I start thinking, well, that is for cofunctions. So I've got negative tangent of pi over 2 minus beta. And tangent you can't drop the negatives for because that's an odd function, but that's going to give me cotangent because that's the cofunction. And they used beta this time, so we want to stick with that variable. And then they have cosecant of a negative beta. So I think about cosecant and about whether or not I can lose it or move it as far as the negatives go. And cosecant is the reciprocal of sine. So I can't lose it, but I can move it. So I'm going to put it out in front. All right, so far what I've done is I've used a cofunction identity, and I've thought about the even and odd. And now, in the numerator, I have a negative times a negative, which is going to be a positive. So I have the cotangent of beta times the cosecant of beta. And then in my denominator, I start thinking about my identities. And cotangent squared plus 1. And I go back to my identities and I see that cotangent squared plus 1 is cosecant squared beta. Like so. And now what I want to do is take a look and see, hey, I can do some canceling here. I have 1 cosecant in my numerator and I have 2 in my denominator, so I'm going to cancel one of those out. So right now I have cotangent of beta divided by cosecant of beta. And those are both secondary trig functions. So maybe I better see what those look like in terms of sine and cosine. And cotangent is cosine of beta over sine of beta. And I need to divide that by 1 over. Cosecant is the reciprocal of sine. So that'll be the sine of beta. We know that we absolutely do not divide fractions. We multiply by the reciprocal. So cosine of beta over sine of beta times sine of beta over 1. And now the sine of beta will cancel out. And I get cosine of beta, which is obviously a single trig function. that we managed to get. And again, that all came from that negative tangent of pi over 2 minus beta, cosecant of negative beta over cosquared beta plus 1, cotangent squared beta over 1. Now, one of the things I wanted to mention here is, notice how I decided to go with vertical work with this problem, and I just kept going vertical the whole way. What you need to do is have your work organized so that it's easily followable. So you have to decide if you're going to do your work up and down, like this, which is the vertical, or if you're going to go horizontally. And you definitely have to have the equals on there to show the equivalent expressions as you move from one step to the next. And you absolutely cannot skip steps. Easily followable work is what we have to see, because remember, what I'm really testing is, what was your thinking? Was your thinking correct as you were going through all of this work? And now we're at solving trigonometric equations. So this is another part of our objective, and we have simplifying expressions and or rewriting them in more useful equivalent expressions is very helpful when trying to solve trigonometric equations algebraically. Boy, is it ever. So we want to have things simplified. Now, example 6 says, solving a trigonometric equation, find all the values of x in the interval from 0 to 2 pi. So that means I have to think about one full rotation where these answers are going to be at. And it says that solve cosine cubed of x over sine of x equals cotangent of x. So here's what we need to do. We have to think, how are we going to get this to help us out? And I see that I have a cosine cubed of x in here, and I need to figure out how to go from there. So I'm going to go ahead and treat this as if it were a proportion, and I'll have cosine cubed of x equals the cotangent of x times the sine of x. And then the next thing that I want to do is see, in terms of sine and cosine, what's going to happen over there on the right hand side. And that's because I have cotangent, which is a secondary trig function, and cotangent is cosine of x over sine of x. And I have to multiply that by sine of x, and I realize, well, sine of x is going to cancel out. So this is really going to be cosine cubed x equals cosine of x. But what I really am looking forward to is being able to factor, because I have that cosine cubed of x. So what I'm going to do is I'm going to subtract the cosine of x from both sides. And get it equal to 0 so that I can factor. So we treat these like polynomials, even though they're trigonometric equations. We're going to factor out a cosine of x, and we'll get cosine squared x minus 1 equals 0. The blue is giving me trouble again, so I'm going to give it just a second to turn on here. And I want you to remember, here's our really basic Pythagorean identity right up there. Sine squared x plus cosine squared x equals 1. Now what we want to do is know what we should substitute in for cosine squared x minus 1. And I realize, well, that's kind of backwards. You know, before we were able to just subtract cosine squared x from both sides and use that. But this one is definitely backwards. So what I would have to do is subtract a 1 from both sides. And then I'd have to subtract a sine squared x from both sides. So that'll give me cosine squared x minus 1 equals negative sine squared x. So now it looks like this. Cosine of x times negative sine squared of x equals 0. And it is in factored form. I can see that. So how do I get my zeros? Well, my zeros come from either cosine of x equaling 0 or negative sine squared of x equaling 0. And that's because 0 times anything will give me 0. So I have two mini equations to solve here. I need to know when cosine of x equals 0. And I need to know when negative sine squared x will equal 0. So now I move to solve those. And I remember this was all talking about from 0 to 2 pi. Well, finding 0 is going to be a quadrantal. And I remember that those ordered pairs come cosine theta, comma, sine theta. So I see my zeros for cosine right here and right here. And that's pi over 2 and 3 pi over 2. So there are 2 of the solutions. And then I have to figure out, well, when is sine squared x going to be 0 or negative sine squared x? But the first thing I do is divide both sides by -1. And that's not going to do anything to my little 0 over there. It's still going to be 0. So sine squared x equals 0. If I take the square root of both sides, and I remember my little plus or minus, I realize, well, that's not going to do anything either, because plus or minus the square root of 0 is just 0. So I go back to my unit circle drawing, and I realize, well, these ordered pairs are always x is cosine and y is sine. And I see that I have zeros at 0 and pi. And then I check my answer. And the reason that I'm definitely checking this one is because this started with a fraction. And whenever we have a fraction, there's a possibility that we may make it undefined by the denominator equaling 0. And that means those 2 answers I just found that made the sine of x equal to 0, I can't use those. Those would be undefined because they're going to go in the denominator. So these are not solutions. 1 strike is enough, but I used a big X there because I'm, well, making a point. And these 2 in our 0 to 2 pi are definitely going to be the solutions to this example. So checking, kind of stopping to think about the entire problem holistically is going to help you out a lot. Example 7 says solving a trigonometric equation by factoring. So find all of the values of x in the interval from 0 to 2 pi so that 2 sine squared x plus sine of x equals 1. My hope would be that we would have thought of that without their little hint, but definitely that's going to help us. And again, we want to know from 0 to 2 pi, what are those solutions? So all the way around one rotation. So I see 2 sine squared x plus sine of x equals 1. And I think I'm going to move that 1 over and see if this isn't factorable here. Well, let's see. Not used to factoring with sine, but pretty obviously I'd have to have 2 sine of x and 1 sine of x to multiply to 2 sine squared of x. And then in the back, I need 2 numbers that are going to multiply to -1. Well, that's just -1 and +1. But somehow give me 1 sine of x in the middle. So I think, well, if I put a +1 here, that outside times outside would give me 2 sine of x. And if I put a -1 there, inside times inside is a -1 sine of x. And 2 minus 1 is 1. And that will do it. So now I see the 2 factors here that would give me my zeros. This one and this one. So the 2 sine of x minus 1 equaling 0 by the zero product property would make this work. And the sine of x plus 1 equaling 0 by the zero product property would also make this work. So let's go after the first one. We'd add a 1 to both sides and divide by 2. And hopefully you'd think right away, ooh, that's got to be a 30, 60, 90. Whether or not you draw it or not, totally up to you. But I want to make sure everybody understands how we're getting that. So if we want the sine of x to equal 1/2, that means that we're talking about an angle that has an opposite of 1 and a hypotenuse of 2. And that's our 30-degree angle, which would be pi over 6. So there's one of the solutions. But remember, as we go around a full 2 pi, there is another positive sign somewhere. And in fact, it's in quadrant 2. So in quadrant 2, we have to think about placing that pi over 6 right here, so that'll be our reference angle, and then giving it its new name from the positive x-axis, and that would be 5 pi over 6. In the other two quadrants, sign is negative, so we're not going to find any more solutions there. Now let's go after the other 0, which was sine of x plus 1 equals 0, and if we subtract 1 from both sides, we'll have sine of x equals negative 1. And the sine of x equaling negative 1 hopefully makes us think, well, that can't be a 45, 45, 90, because opposite over hypotenuse can't be 1 over 1. That must be quadrantal. So I need sine of x to equal negative 1, and there's only one place where that's going to happen, because again, each of these ordered pairs are cosine theta, comma, sine theta. That's right there, and that's 3 pi over 2. So we have 3 solutions here: pi over 6, 5 pi over 6, and 3 pi over 2. We are solving, which was a big part of one of our objectives. Now B says, let's change this. Let's talk about all the solutions to the trigonometric equation 2 sine squared x plus sine of x equals 1. Hold on. So now we're saying even the coterminals, which means I'm going to have to come up with a formula for this. So I'm going to use my number set notation. X will be defined as x equals, well, I've got the pi over 6. Is there some easy way that I can make that continue on again and again that would maybe hit the 5 pi over 6? Now, the only way that's going to happen is usually if we look at pi over 6 and 5 pi over 6 and we see a difference of 1 pi or 2 pi between the two. And that's not happening here. We've got a difference between that of 4 pi over 6, which is 2 pi over 3. So I'm going to have to do these separately. I can't come up with a nice formula that would cover both of them. So x equals pi over 6 plus the coterminals, which would be 2 pi n, where n is the set of all integers. And x is defined as x equals 5 pi over 6 plus 2 pi n, where n is a set of all integers. And then that 3 pi over 2, that's kind of standing out all by itself there. But again, we have to cover all the coterminal angles. So that will be 3 pi over 2 plus 2 pi n, where n is the set of all integers z. And now we have it. So there's our first time of writing all solutions down, because we don't just have the originals that we found from 0 to 2 pi, but we're explaining that coterminally this is going to keep going around and around and around, and we are going to see those answers again. Now we have some more. So I know it says rapid fire, but you guys are just starting off with these, so I don't expect this to go super fast. The good thing here, it says solve each of the following such that we're staying between 0 and 2 pi. So we're not going to come up with any fancy formulas for these. We're just going to figure out what we have in one rotation without a calculator. So I'm looking at A, and I think, you know what? I think I can solve that for sine of x. I think if I subtract the square root of 3 from both sides and divide by 2, yeah, I think I know that one. I think that's a 30, 60, 90 triangle. And for my 30, 60, 90, sure enough, I see all the numbers that are going to work there. Trying to find a little spot where I can fit my Cartesian coordinate plane to put on my pluses and minuses, and I think I'm going to have to go here. There we go. Because I need to know when is sine going to be negative, and sine is going to be negative in the third and fourth quadrant down there. So let's go back to figuring out what the angle is, and then we'll place it in third and fourth quadrant. So sine is opposite over hypotenuse. To get the square root of 3 to be an opposite, we would have to be at the 60-degree angle. So now I know that my focus is on pi over 3, because 60 degrees is pi over 3. But I have to put it in third quadrant, which would be 1 pi plus pi over 3. So that's 4 pi over 3. And I have to put it in fourth quadrant, which would not be all the way around, which would be 6 pi over 3 or 2 pi. It would have to be 5 pi over 3. So we have two answers. X equals 4 pi over 3 and 5 pi over 3. Well, B looks very similar. So why don't we just try and solve this one that way? So it'll be secant squared x equals 2. All right. Well, what can I do with that? Well, I certainly know that secant is what you get when you flip cosine. So how about if we just flip both sides and say cosine squared x equals 1 over 2, which is 1/2. Well, now I'd have to take the square root of both sides, and that will give me the cosine of x equals plus or minus, well, the square root of 1 is 1, and I'll have the square root of 2. Wait a second, I think I know that triangle. Normally we see it as the square root of 2 over 2. But that's going to be 45 degrees. So if you need to, draw the little triangle so that you can see that the cosine being adjacent over hypotenuse, it's a 45-degree angle. But the good news is this one had both positive and negative. So now that means we can go in any of the 4 quadrants with our 45-degree angle. And our 45-degree angle is pi over 4. So first quadrant, it'll be pi over 4. As a reference triangle and a reference angle in second quadrant, that will be 3 pi over 4. Going to third quadrant, it would be pi plus pi over 4, which is 5 pi over 4. And then going into fourth quadrant, it's just shy of the 2 pi, which would be 8 pi over 4. So we have to take one of those away, and that will be 7 pi over 4. So there are the 4 solutions: pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. See if I can move that down just a little bit. There we go. Alrighty, off to C. And C, again, I think, you know what? If I can just get cosine squared to equal a number, maybe I can figure this out. So I add 3 to both sides and divide by 4. And then I take the square root. And again, it's the positive and negative square root. Square root of 3 is going to have to stay the square root of 3, but the square root of 4 is 2. And I recognize that. I've got the square root of 3 and a 2. That's what happens in a 30, 60, 90. So I go back over to my 30, 60, 90 drawing, and I think if adjacent is the square root of 3, that has to be a 30-degree angle. And 30-degree angle is pi over 6. But because it has a plus or minus, I can go in any of the 4 quadrants. So in first quadrant, it's pi over 6. In second quadrant, 5 pi over 6. In third quadrant, 7 pi over 6. In fourth quadrant, it won't be 12 pi over 6 because that's all the way around. It'll be 1 shy of that, which will be 11 pi over 6. So notice I'm not trying to draw all of those all the time. I'm trying to picture visually what's happening here in the coordinate plane so that I don't have to write all of those down. And that has to do with our understanding of those fractions and where that pi comes from as equaling 180 degrees. D says sine of x has to equal cosine of x. Oh, well, I think I'm just going to stop right there. When does sine of x equal cosine of x? It's only going to equal it. They both have something over hypotenuse. So that's already equal. So it's only going to work if opposite and adjacent are exactly the same thing. Well, that's a 45, 45, 90 when that happens. And to get sine and cosine to be the same, we would be talking about our 45-degree angle, which would be pi over 4. So I have my little pi over 4, and then what I have to do is figure out, well, where else is this going to happen, where both of these will be exactly the same. Well, they were both positive in quadrant 1 for pi over 4, and then I have to see where sine and cosine both have the exact same sign in the quadrants, and I see that that's quadrant 3. So I think about my little reference angle of pi over 4 in quadrant 3, and I realize that will be 5 pi over 4. Now that is the best way to solve this problem. If you try any algebra on this one by squaring both sides or anything like that, you're going to end up with some extraneous solutions. So try to think basic when you see something that is very basic. And when it said sine of x equals cosine of x, that's a very basic problem. Whereas with E, not quite so much. We've got a 2 going there, a cosine squared x, and a cosine of x, which hopefully makes you think about factoring. So let's subtract cosine of x from both sides. And let's factor. We'd have to take a cosine of x out, and that would give us 2 cosine of x minus 1 left in our parentheses. And now using the zero product property, either the cosine of x is going to equal 0 or 2 cosine of x minus 1 is going to equal 0. So cosine of x equals 0. Think about quadrantals. And remember that cosine is the x in those ordered pairs. So if we want cosine of x to equal 0, we've got to go with pi over 2 and 3 pi over 2 for one full rotation. Now for my other 0, my 2 cosine of x minus 1, we would add 1 to both sides, and then we would divide by 2 and get 1/2. And 1/2 we should recognize from our 30, 60, 90 triangle. So I come over here to the triangle and I see adjacent over hypotenuse. That would have to be a 60-degree angle, which is pi over 3. But cosine is positive in 2 quadrants. And if we go back up here to the top, we see that cosine is also positive in 4th quadrant. So I think, well, what's going to happen if I put my little pi over 3 right here? What would that be called? Well, all the way around would be 6 pi over 3. So I'm 1 short of that, which would be 5 pi over 3. Out of space, so I wanted to make sure I moved this one. And as I take a look at it, I see, well, it has both cosine and sine. That's no good. So I think for a second, if I could substitute something in for sine squared that had to do with cosine, and pretty obviously I can if I just subtract cosine squared x from our Pythagorean identity. So I'm going to substitute 1 minus cosine squared x in for that sine squared x. And now I start thinking, hey, I should be able to factor this. So if I subtract a 1 from both sides and add a cosine squared x to both sides, I will have, and putting this in order, standard form basically with the highest power first, I'd have cosine squared x plus 2 cosine x, and then I'd have a plus 1 because 2 minus 1 will give me 1 equals 0. All right, so let's see if we can get this one factored. Well, this looks like y squared. This is 2y, and this is a 1, and if this is y squared and this is 1 squared, I wonder if this isn't one of those perfect square trinomials. And how we check that is by taking y times 1 and doubling it, and if it matches the middle term, then it's a perfect square trinomial. And sure enough, it is. 1 times y times 2 is 2y. So this is really going to be y plus 1, the quantity squared, equals 0. But I have to put my cosines in there. So this will be the cosine of x plus 1 squared equals 0. Now, if you're thinking, I wouldn't have gotten that Cederholm, I would have written it out as one set of parentheses cosine of x plus 1 and another set of parentheses as cosine of x plus 1. Big deal. You're going to get the same answer. Because what we know at this point is we need to take the square root of both sides, and we'll have cosine of x plus 1 plus or minus the square root of 0 is still going to be 0. We'll have to subtract 1 from both sides, and then we realize that's got to be a quadrantal. So we think about where we're going to have a cosine that is -1. And remember, these ordered pairs are cosine, comma, sine, and there it is at pi. So there is our solution. And that is a great place to stop. We've done a lot of solving, which was a huge part of our objective. And there is Pre-Calc 5.1 Day 2. And we did do examples 4 through 7. And we'll work with the graphing calculator stuff and the other solving that we have that looks really interesting as you look at those last few problems when you come back on Monday. Have a great weekend.